Welcome to AI Paper Slop. We are skipping the intro music, skipping the pleasantries, and jumping straight into a paper today that fundamentally exposes how you should be building automated scientific workflows.
Right, yeah. Let's just get into it.
So the paper is called Deterministic Access to Global Viral Sequence Data Enables Robust Agentic Scientific Discovery. And this is by Nasri, Gurev, and a team of researchers from the Hasso-Plattner and Broad Institutes.
And the core insight we are really tackling in this deep dive is that your state-of-the-art AI research agents, so we're talking Claude, GPT, Bioinformatics, they are currently failing catastrophically at retrieving viral genomic data directly from databases like NCBI.
Because those portals are optimized for human web browsing, not programmatic access.
Exactly. And because of this, agents just completely hallucinate pagination tokens, they hit infinite timeout loops, and they silently drop crucial training data.
Right. And to actually prove this was happening, the authors built VirBench, which is this benchmark of 120 curated queries. And I mean, without a dedicated retrieval tool, Claude Sonnet 4 hit an abysmal 16.9% accuracy.
Which is wild for a frontier model.
Yeah, totally. And even GPT-5.5, which is the absolute best of the bunch, maxed out at like 91.3%, with heavy run-to-run instability too.
So the authors built a solution. They built Gget Virus, which is an open source Python tool that provides a strict deterministic API layer.
And the results are crazy. When they instructed the agents to use this tool, GPT-5.5 hit 99.7% accuracy. Downstream workflows completely stabilized, and data transfer volumes dropped by like 98%.
Yeah, so the immediate takeaway for you, the ML engineer listening right now, is just that your autonomous scientific agents are really only as reliable as the deterministic data retrieval layers you provide them.
That perfectly sets the stage. But to actually understand how to bulletproof the agentic pipelines you're building right now, we kind of need to look under the hood at how data retrieval silently poisons downstream tasks in the first place.
Right, the silent killer.
Exactly. And it starts with the architecture mismatch at the National Center for Biotechnology Information, or NCBI. Practically every automated bioinformatics pipeline starts there.
Oh, okay.
Right.
Yeah, whether you are doing vaccine antigen design or just viral surveillance, it all relies on the NCBI Virus portal.
But as an engineer, you might look at that NCBI web portal and think, well, great, it has 50 different metadata filters. I'll just point the LLM at the API and let it write the fetch requests.
Which makes sense on paper.
Right. But the NCBI Virus web portal isn't actually a single database. It's an aggregation layer. It's like asking an LLM to scrape a highly dynamic, JavaScript-heavy website to order a specific pizza, rather than just giving it a clean GraphQL endpoint.
Yeah, that is a great analogy. It is pulling synchronized data from GenBank, ResSec, the Sequence Read Archive, and several others. So the human-facing web interface, it handles all this complex combinatorial filtering beautifully.
Like taxonomy, host species, geographic location, things like that.
Exactly, collection date, sequence length. But the underlying raw APIs, like Entrez or the newer datasets REST API, they natively support only a fraction of those parameters on the server side.
So the LLM receives an instruction that requires filtering by, say, a specific host species and a specific geographic region, and realizes the API endpoint doesn't accept those specific parameters directly in the URL query.
And that is where the trouble starts.
But wait, my immediate instinct as an engineer here is to just bypass the API's filtering limitations entirely. I mean, compute and bandwidth are incredibly cheap right now. Why shouldn't the frontier model just write a Python script to brute force, download the entire raw data set for SARS-CoV-2, and then filter it locally in memory? Why are we treating this like a complex problem?
Well, because brute forcing a multi-terabyte biological database exposes the specific mechanical weaknesses of LLM state tracking. We are not talking about downloading a simple CSV file here.
Oh, right. We are talking millions of records.
Millions of deeply nested XML or JSON records. If your agent tries to download everything just to find a handful of specific sequences, it has to navigate pagination limits. The APIs typically batch records at 1,000 per page.
Which means the agent has to write a while loop to iterate through the requests.
Yes, and it has to maintain the state of that loop across thousands of network calls. LLMs have a finite context window, and they struggle immensely with iterative state tracking over long, continuous API interactions like that.
Especially when the API limits you to 1,000 records per page for a 2 million record database.
Exactly. The agent has to parse the JSON response, extract the next page token, pass it to the next request header, handle transient 502 gateway timeouts.
Manage rate limits.
Right, manage rate limits, and append the data without blowing up its own memory constraints.
So it inevitably loses the plot. The context window degrades, it loses the variable name for the token, or it just flat out hallucinates an exit condition.
Or it simply terminates the loop after 50 iterations because the API hung up for 5 seconds and the LLM just interprets the timeout as the end of the database.
Wow. And this is the silent killer I really want to highlight for the ML engineers tuning in. Think about the agents you are running right now. If a standard hard-coded script crashes, it throws a stack trace. You see the error, you fix the bug.
It fails loudly.
Exactly. But when an LLM agent terminates an API loop early, it doesn't throw a runtime error. It just confidently hands you back a dataset of 10,000 viral sequences. It's formatted perfectly. It looks completely plausible.
But you never realize your training data is compromised because you have no idea there were actually 15,000 sequences matching your criteria out there.
So you train your model on an incomplete representation of the viral landscape.
Right. And those missing sequences might contain a critical escape mutation or a new variant lineage. Your entire pipeline is fundamentally compromised at step 1, and the downstream variance in your model's biological interpretation is just massive.
So if the APIs are silently dropping data without throwing error codes, how do you even prove the LLM is failing? You can't just look at the logs and see a crash. You need an objective ground truth.
And that is exactly why the researchers had to build VirBench. They needed to catch the models in the act.
So let's talk about VirBench. It acts as this highly controlled trap, right?
Yeah, it consists of 120 manually curated queries spanning 40 different pathogens, and the ground truth counts for these queries weren't generated by another LLM script.
Well, that's smart. So they didn't just use GPT-4 to grade GPT-4.
No, they were established through manual human execution in the NCBI Virus web interface to ensure absolute deterministic accuracy.
And looking at the benchmark design, these aren't basic find me COVID queries either. They emulate highly heterogeneous, realistic virology workflows.
They require complex combinatorial metadata filters. We're talking queries like find all Lassa virus sequences from Africa collected between 2020 and 2025.
Wow. And the median query required 6 simultaneously applied filters, right? And some went up to 16.
Yes, 16 simultaneous filters. The authors even included 58 queries directly contributed by a diagnostics team building actual physical assays for priority pathogens.
So it's real-world stuff.
Completely real world. The benchmark was deliberately designed to push the agents into edge cases where they couldn't just rely on a top-level taxonomy search.
So they set the trap, they let the state-of-the-art autonomous systems walk right into it without a dedicated retrieval layer, and we get those baseline stats I mentioned at the top.
Right, the bloodbath.
It really is. Claude Sonnet 4, which is normally brilliant at complex coding tasks, hits 16.9% accuracy. Biomni, which is a biomedical agent powered by Sonnet 4, only managed 22.5%.
Pattis analysis hit 40%.
Yeah. GPT-5.2 Pro got 67.1%, and even GPT-5.5 at 91.3% is, that's entirely unacceptable for reproducible science.
It really is.
What specifically caused performance to crater so dramatically the moment you introduced more than 3 simultaneous filters?
Well, the undercounting from broken pagination loops was the primary culprit, like we discussed. But they also failed catastrophically on flexible string matching and domain-specific edge cases.
Okay, can you give an example of that?
Yeah, a perfect mechanical example from the paper involves an influenza, a query looking for sequences from Korea.
I found this part so fascinating because it highlights the gap between how an LLM reads API documentation and how human domain experts actually interact with data in the real world.
Right. There are exactly 3 influenza A sequences that match all the filters for this specific query, and the LLMs failed to find them almost every single time. They failed because they read the API schema literally. The relevant geographic data wasn't in the metadata's designated location field. For those historical sequences, the location field was actually null, and the broader region field simply said Asia.
Oh, I see. So the LLM applies a strict programmatic filter, like if location equals Korea.
Exactly, which evaluates to false, so it drops the sequence from the dataset.
But a human virologist knows that historical sequences often have messy, unstructured metadata. They know the geographic signal is frequently embedded directly in the raw FASTA header or the virus strain name string itself.
Like a /Korea/426/1968.
Right. And the human-facing web portal handles this implicitly, right? Its search bar just sweeps across multiple unstructured fields simultaneously.
But the raw REST API does not. An LLM relying purely on the API documentation has absolutely no way of knowing it needs to write a custom regex script to parse the strain name string just to fulfill a geographic filter.
It lacks the domain-specific intuition to look outside the defined schema.
Right. And beyond those edge cases, the agents also just couldn't handle standard API backend synchronization issues.
What do you mean by that?
Well, certain taxes like mpox or HIV-1, they frequently trigger transient failures on specific API filters due to how the NCBI synchronizes its databases internally.
Oh, so the API itself throws an error.
Yeah. When the API threw an unexpected schema error for an mpox query, the agents simply abandoned the filter entirely rather than writing a retry logic block.
Just skipped it?
Yep, leading to massive data drift.
So the autonomous agents are failing because we are forcing them to navigate an incredibly brittle, human-optimized backend using low-level, unoptimized API calls. It's literally the equivalent of asking an LLM to parse a highly dynamic, JavaScript-heavy website using raw regex instead of just giving it a clean DOM tree.
Or a dedicated GraphQL endpoint. Yeah, it's going to break.
So the authors recognize this architectural flaw, and they build gget virus as a deterministic wrapper to fix it.
Yeah, they integrated it into the gget ecosystem, which is already widely adopted in bioinformatics for its one-line data retrieval philosophy.
And the architecture of gget virus completely bypasses that multi-terabyte brute force download trap we discussed earlier. It achieves this through what they call a staged query optimization strategy.
Let's actually break down the mechanics of that stage strategy, because this is where the engineering gets really elegant.
Yeah, how does it handle a 16-filter combinatorial query without downloading the whole database to memory?
It breaks the retrieval into decoupled steps to minimize data transfer. So step 1, gget virus pings the lightweight dataset's REST API for minimal metadata.
Just the bare minimum.
Right, just the sequence of sessions and whatever broad server-side filters the API actually supports natively, like taxonomy or sequence length.
Okay, then what?
Step 2, it takes that relatively small metadata payload and applies all the complex combinatorial filters strictly client-side.
Ah, so it handles the string parsing, the edge cases, the embedded geographic data locally on a much smaller structured JSON payload.
It's exactly.
It's basically like reading the library index card to make sure a book has exactly what you need before you haul a 1,000-page encyclopedia back to your desk.
That is a highly accurate way to visualize it. It computes a highly precise, validated list of accession IDs locally first. Then in step 3, only after the list is perfectly filtered does it initiate the heavy network request for the actual sequence data.
So the large FASTA files are the deeply nested GenBank XML records.
Right, but only for those specific IDs.
The resource savings from this staged approach are just staggering. The paper details a benchmark query for 2025 SARS-CoV-2 surface glycoprotein sequences. If you try to use the native download then filter method the LLMs default to, you're pulling down 284 gigabytes of data before you can even begin your local Python filtering.
284 gigabytes, it chokes the network bandwidth, it spikes your cloud egress costs, and honestly, it takes hours just to set up the data frame.
But gget virus, using its staged strategy, accomplishes the exact same deterministic result with a 3.8 gigabyte download.
Which is a 98% reduction in storage volume.
It's unbelievable. And because the tool uses streaming execution, so evaluating metadata records sequentially via Python generators and writing them directly to disk without holding the entire object in an array, the peak RAM utilization stays well under 16 gigabytes.
Which means you can run this component of your pipeline on a standard local machine rather than spinning up a massive, expensive, memory-optimized cloud instance.
Oh, that's a huge deal for cost scaling.
Huge. Furthermore, Magnet Virus handles the transient API failures automatically behind the scenes. If it detects that the NCBI backend is temporarily failing to support a host filter for a specific virus, it automatically removes that filter from the API request.
And then just pulls a slightly broader dataset.
Exactly. And reapplies the missing filter client side. It abstracts all the complex retry logic and batch size adjustments away from the LLM entirely.
The agent just asks for data, and the wrapper handles the chaos. So what happens to the agents when we give them this tool? We have this hyper-optimized deterministic wrapper. We took the exact same frontier models that were failing miserably, like Claude Sonnet 4 at 16.9%, and we simply prompt them to use the tool.
Right, and the instruction in the prompt was literally just to pip install virgit version 0.30.3 and read the provided documentation.
That's it.
That's it. And the transformation in agent capability is immediate. Claude Sonnet 4 jumped from 16.9% to 92.8% accuracy.
Wow.
Bioinformatics leaped from 22.5% to 90%. GPT 5.2 Pro hit 98.9%. And GPT 5.5 reached 99.7% accuracy.
Guy day. And just as importantly, the tool calls plummeted. The agents weren't thrashing around writing dozens of iterative scripts to fix pagination errors anymore. GPT 5.5 went from needing nearly 15 tool calls per query down to just 4.5.
It made the entire process faster, drastically cheaper in inference costs, and highly stable. That run-to-run variability we saw earlier effectively just vanished.
The pipeline actually became deterministic.
Yes, but I want to zero in on a crucial detail for the engineers designing these systems right now.
Okay.
GPT 5.5 hit 99.7% accuracy with the tool. Why didn't it hit 100%? If Virus is a perfectly deterministic retrieval layer, where are the residual errors coming from?
Yeah, I was wondering about that. If the tool hands the agent the exact correct answer, how does the agent still manage to mess it up 0.3% of the time?
Well, the remaining errors were not retrieval failures by the tool. They were LLM processing failures. The agents suffered from what we could call the overeager assistant problem.
The overeager assistant problem.
Yeah. They received the perfectly filtered output from Virus, but their inherently probabilistic nature drove them to try and redundantly reprocess the data.
Oh, no. So they try to be too smart. They don't just accept the FASTA file. They write a pandas script to open it up and double-check it.
Exactly. They would attempt to reapply local filters to the already perfect data. In doing so, they would import pandas, read a FASTA file as if it were a CSV, misalign the columns, and arbitrarily drop half the sequences because of a missing delimiter.
That is so frustrating.
Or, despite having explicit documentation, they would hallucinate non-existent parameters when calling the tool, assuming it functioned like a completely different bioinformatics library they saw somewhere in their training data.
It's incredibly frustrating to watch an agent get handed the correct data set on a silver platter, only for it to say, hold on, let me write a regex to double-check this formatting, and then it completely corrupts the file.
Yes.
This feels like a universal lesson for agentic architecture, regardless of the specific domain you're working in.
It really is the defining lesson. The actionable takeaway for you as an ML engineer is twofold here. First, you must formalize your data retrieval layer as a strict programmatic operation. Do not let the LLM write the fetch logic.
Right, use a wrapper.
Second, you have to explicitly prompt your agent to step back and trust the deterministic tool's output. You have to write system prompts that actively discourage brittle post hoc processing. Do not let your LLM overthink what the deterministic layer has already solved.
That tension between probabilistic reasoning and deterministic execution really is the core challenge of building autonomous systems right now. Scaling up LLM parameters doesn't magically fix an inability to navigate a human-optimized web portal.
No, it doesn't. A non-deterministic data retrieval layer means your entire agentic workflow is just built on shifting sand. You cannot achieve reproducible automated science if the foundational dataset changes every time the API decides to hang up for 2 seconds.
Which makes sense.
This paper proves that deterministic programmatic infrastructure is a strict prerequisite for scientific discovery.
And there's a broader context here regarding the dual-use nature of these tools, right? Which the authors do explicitly address in the paper. By replacing brittle, failure-prone LLM scripts with a highly optimized Python wrapper, you significantly lower the barrier to entry for interacting with global viral sequence data.
It's a massive acceleration in capability. I mean, during the early days of outbreaks like SARS-CoV-2 and Mpox, data access and curation were severe bottlenecks.
Researchers spent weeks just formatting data.
Right. Tools like gget Virus eliminate that friction, which is phenomenal for global health response. But operating on public data with automated, agent-driven pipelines undeniably amplifies capabilities.
It's a double-edged sword.
Yeah, as these deterministic tools become standard in autonomous biological workflows, it absolutely necessitates thoughtful governance and security frameworks from the institutions deploying them.
You are giving frontier models frictionless access to the underlying code of biology. It is an incredibly powerful lever, and as this paper shows, it is now very easy to pull. Which brings me to a final thought for you as you look at your own architecture today.
Yeah, this is the big question.
We just saw how a lack of deterministic APIs completely hobbled the most advanced models in the world when it came to virology, and how a targeted, well-engineered Python wrapper fixed it almost entirely. So look at the data pipelines you're building right now, whether you are working in material science, quantitative finance, legal tech, or fluid dynamics. Where is the human-optimized web portal bottleneck silently corrupting your training data, just waiting for a deterministic wrapper to unlock your agent's true potential?
It's definitely out there.
Something to think about as you review your own architecture this week. Thanks for joining us on this deep dive. Keep your models sharp and your data deterministic.